So let me give you a quick motivation of why I think deep learning or machine learning can actually play an important role, but why it cannot play the role alone. So it doesn't start too nerdy. It starts very general, and probably I'm talking to the, I'm preaching to the Pope here. Our target also at the Institute, and many of you, is basically the Earth system. And what's so special about the Earth system is, and that's something that we actually also have to emphasize always in the Max-Planck Society, that it is a complex system where biological, chemical, and physical processes interact with each other, and it is a, as far as we know, unique system, so we cannot do like repeated experiments on the whole Earth to do science. So we have to rely on observations, on things that are happening, natural experiments, and that is quite different, for example, from research related in medicine or physiology, where you have replicate mice and so on and so forth, even if this is ethically also, of course, sometimes problematic. So it's in the realm of complex system science where we are. That's a very challenging topic overall. There are no relativistic effects, no quantum mechanics really involved, but complex systems. And one of the properties is basically that we are spanning a hierarchical system from molecules via ecosystems to the whole globe, which spans, for example, 17 orders of magnitudes in space. And that, if you have such a complex system, you want to analyze it as a subset of interacting subsystems. In the Max-Planck Society, we have this Earth system science as well established. And this is from a Max-Planck research journal, The Intertwined Earth, basically interwoven Earth, depicted here as this ball of wool. And of course, the different spheres, we know them from undergraduate studies: atmosphere, biosphere, hydrosphere, and the cryosphere. And then also as a center of research here, of course, the humans as a factor. There's now the term Anthropocene being termed and almost fully established. And we can see actually the activity of the humans, for example, by the night lights in the satellites. So it is easily visible. And the system comes now about, of course, through the interaction of these different spheres. In the Earth systems, on the one hand, exchange of trace gases like carbon dioxide and water, and on the other hand, exchange of energy, latent sensible energy, that basically keeps our Earth at the temperatures that we are currently having. Of course, there is also exchange of information, but in this context doesn't play such a big role. So this is really if you want, a little bit of a reductionistic view on the Earth already, so decomposing it into different spheres, and that has been the foundation of Earth system modeling. I call it also a bit of the reductionistic dream, wiring all together. You don't need to read everything here. It's a, I think, quite famous Brotherton diagram from Chris Brotherton in the 80s, where exactly this is being shown. We have these different components: marine biogeochemistry, terrestrial ecosystems, atmosphere, tropospheric chemistry, and so on and so forth. And these things interact with each other according to physical and chemical and partly biological laws. And the idea is, once we have all these first principles wired together, we can predict the Earth system and understand the dynamics. And of course, this is important to do so. It's actually the only chance to really predict the future. But the dream has, to some extent, come. Well, I don't want to say nightmare, that would be too strong, but there's actually quite a crisis in this Earth system modeling, because if we particularly look at the development of the carbon cycle and the carbon cycle climate feedback, Pierre Friedrichstein already 2006 has done this analysis of different models where these models predict into the future how much carbon dioxide will be taken up by terrestrial ecosystems. Now they are taking up roughly 1/4 of our emissions, a little bit more. And you see here the different trajectories of the models. And you see that they vastly diverge in the future, but they agree for the past quite well. At least the range is much smaller, and in the future, some models say, well, there will be a strong further increase of the uptake, while others actually say that the carbon sink will actually turn into a source. So here, negative numbers, which will then actually cause a positive feedback. So even increasing the greenhouse gas effect. This is that really looks quite frightening, but I don't know if here are any people that actually question the climate change at all. One should stress the point, despite these uncertainties in the modeling, which is really a severe scientific problem, there's no question, of course, about the relationship between the CO2 emissions and the temperature change. You see basically here this linear relationship. Do we have a pointer somewhere? No, I don't think so. Okay, then I will try. And you see basically this range from here to here is basically in our hands, depending on how much we actually emit in the future. But there is something. Oh, thanks a lot.
The big one.
Ah, the big one. Okay. But there is also still quite some uncertainty. Let's say, given a certain emission, there's still some uncertainty on what the expected temperature change will be, or if we want to reach a certain temperature level like 1.5 or 2 degrees, you see also the allowed emissions kind of that lead to that are also not totally certain, and that is caused by the feedback. Maybe just one thing. I think it's really important to know that this is not just an academic question, these uncertainties, but well, that is an estimate by Chris Hope, who basically said it's a 10 trillion value of information about a better understanding of this transient climate response and the feedbacks. In any case, this situation, these uncertainties, and this crisis in the modeling, in the classical climate and Earth system modeling, has actually led us to think about that a bit more, and led to this perspective paper that possibly has been the reason to invite me here for a talk. And it basically starts from the notion that we are actually in a situation of unprecedented system data. We are in an era of big data, and this is really, let's say, or the Earth system is really prototypical for big data. There are the 4 V's of big data: volume, velocity, variety, and veracity. And all of those boxes present strong challenges, in particular in the Earth system science context. I think actually the most severe one is probably in this variety, which is also depicted here in the central figure, because we have very, very different and heterogeneous data streams, from point data of ecosystem level observations to global observations from satellites, where every spot on Earth is revisited every day or every couple of days, and then atmospheric measurements and hydrological measurements, ocean measurements that often integrate over larger areas. So this is kind of also to motivate data science people to work on Earth system questions, and not to work on recommender systems for Amazon or on Netflix. And I just want to give you a quick example and make the point that data-driven science, of course, relies on data, and we need really good, not only big data, but also rich data. And this is just a personal example. Many of you may also know this effort of FluxNet, where actually the exchange of carbon dioxide, water, and energy between ecosystems and the atmosphere is observed at half-hourly timescales at a large range of stations globally, so that we can get a kind of very diverse picture of different ecosystems, how they respond to climate variability. This rich data leads to, as I said, half-hourly data and to very characteristic information on different ecosystems. Here is just the carbon dioxide exchange shown as so-called fingerprints, or classically one would say isoplace diagrams, where we have here the time of the day and time of the year. And then you, of course, see the tropical rainforest is basically active throughout the year, taking up carbon during the day, releasing carbon during the night, while, for example, the European beech forest starts very abruptly end of April when the leaves are coming out, and then also stops relatively abruptly in autumn when the leaves fall down again. And another system like the Mediterranean savanna is in principle also active all year round, but you see in particular here reduced activity by the lighter colors in summer, late summer, when the system is dry. So you can see from that basically a lot of information on annual, hourly timescales and through many decades, and this behavior can be, of course, extracted, and one can try to better understand with this data how ecosystems respond to climate variability. On the other hand, if you want to look at the Earth system and as a globe as a whole, you can easily estimate that these stations, which are maybe 500 globally, each covering 1 square kilometer, so we are basically covering 500 square kilometers of the Earth, which is less than 1 per mil. So we cannot have a direct information from those stations on the Earth system, and that's where actually now the interplay with other data streams come into play, and that's what we call scaling from flux towers to globe. Here depicted in this diagram of spatial scale and temporal scale, where we can see where different observation systems actually have their domain, and these ecosystem observations, they operate now for a couple of decades and cover, as I said, a spatial scale up to one square kilometer, so far away from the global scale. But on the other hand, we do have satellite Earth observation, and this one can actually give us information for the whole globe in a very consistent and objective way. But it doesn't observe exactly the processes in the ecosystems, like exchange of carbon dioxide and water, that's happening basically at a minute scale. So it's more observing the electromagnetic interaction between of the ecosystems and the, for example, solar radiation. So the idea is basically to use this intersection here where of both scales and extract the joint information from these two data streams, build a statistical model that basically links the satellite observations to the ecosystem observations, and then be able, with a statistical model, machine learning approach, and it can be different ones, to get a global picture of how the ecosystems exchange carbon dioxide, water, and energy, and that is kind of the result, what we call a data-driven view on the dynamic biosphere-atmosphere exchange. It's kind of the first time that one has been able to create those kind of dynamic pictures of the Earth just based on data, not based on models. We see here primary production. We see here this typical activity, of course, in summer in our latitude, but we also see quite some monsoonal systems, monsoonal dynamics that are driven by water availability, and also very clearly a lot of dynamics in the tropics and even in the inner tropics going on that can be basically extracted with this kind of machine learning approach. And well, then we see covariation of carbon fluxes and water fluxes, sometimes anti-correlations with the sensible heat fluxes. So it's a really synoptic view that we get from this data-driven approach. And again, it is basically derived without any theoretical assumptions. And that's why it has been also used quite a lot together with process models to evaluate these process models, and these data sets are now part of benchmarking activities for the process models. So real climate models that are in the IPCC report. And here's just one example. You see here, of course, our products also have uncertainties, but the uncertainties here for photosynthesis by latitudinal bands are much lower than, for example, the range of process-driven models that have been used here in this comparison. Yeah, and that has actually nicely led then also to further development of those process-driven models, how the light transfer in the canopy is modeled, how the nitrogen cycle is modeled, and so on, and so forth. But this is kind of, if you want, old stuff. It's more like showing the potential of machine learning. But clearly, if you think about it, what we have been doing here, it was really just a regression approach. So instantaneous fluxes of carbon dioxide and water have been predicted by instantaneous remote sensing variables. So really a mapping of the present or on the present, if you want. And dynamic effects, like effects of cold spring or droughts and so on, have only been considered with either state variables that come from remote sensing or with so-called hand-designed features where one doesn't use a precipitation itself as a predictor, because if a system is active or not doesn't depend on if it's raining on this day, but it depends on if it has been raining the last month or not. So one can use this, one can design certain variables like soil water content proxies and so on and so forth. That's what we call hand-designed features. But one is it's a little bit arbitrary what one is doing here. So that is what one criticism one can have, and then also the spatial context is not considered. So it's a pixel by pixel prediction, and interactions between pixels have not been considered at all. Another realm of where machine learning plays an important role is not so much prediction, but rather detection. And just give you one nice example because it's such a nice animation. There, the challenge is basically to understand where the Earth system, when and where the Earth system is exhibiting a strange, let's say, behavior. And strange behavior means not only just a heat wave, oh, it has been very hot here, but rather looking at the constellation of many variables, so looking at multivariate detection of anomalies. And we work with this kind of concept of data cubes. Is very simple when we have several variables and they span, of course, in space and in time. And we have kind of synoptic view of many variables and can then look when multivariate constellations are strange. And here's then just one example. We now scan through this data cube. You see here basically now tagged kind of the voxels for the European case when there have been extreme constellations. And this really just derived just from the data that is out there as observation data and derived products. And here is an exemplary example, then the detection of the Russian heat wave that is of course well known, but where not only the heat was very strong, but also other variables have been quite abnormal, and then with all these impacts that I think you know quite well. But then you can do further analysis. I don't go into detail here, but where we can then actually see that the biosphere is actually responding to this heat wave in quite different ways, like negative responses here in the southern part and positive, very anomalous positive responses in the northern part. Okay, But also here, machine learning has been used, but again, spatial context is not really used here, but rather we look at multivariate anomalous situations on a pixel-by-pixel basis, and then they are just connected into these spatial temporally connected components. So how do we bring in spatial and temporal context? And this is really where deep learning comes into play from the machine learning point of view. And there's an extreme analogy between classical machine learning tasks and what are the needs in Earth system science. If you look at classical machine learning tasks, one is object classification and localization, like, okay, this is a cat, this is a dog. And that really maps onto classification of patterns like hurricanes from these kind of continuous fields of multivariate variables. So here we have red, green, and blue channels. Here we have maybe 10 different atmospheric variables that we need to use for this classification. Or super resolution, trying to enhance the resolution of images, is an active field of deep learning research. And that, of course, relates very strongly to statistical downscaling and blending. These are two examples that are kind of static, so not necessarily changes in time. And that is, of course, a very big challenge to bring in the dynamic dimension as well. And there we have video prediction, so trying to predict future scenes in a video, and that relates very strongly to predicting in a short term weather or biosphere states, so very, very important, like seasonal forecasts or extended weather forecasts and so on and so forth. And for time series analysis, this relates very strongly to so-called sequence modeling in machine learning. And one example is language translation, where your meaning does not only depend on the current word, but also on the context, on the words that have been said before. And that is, again, the same thing for ecosystems, for example, where their behavior does not only depend on the current situation, but on previous situations like disturbance and so on and so forth. So there's a very strong analogy here, and where the idea would be to use these methods also to understand dynamic effects in ecosystems. Yeah, so so this is very general. I actually personally convinced myself a couple of years ago in mini sabbatical in Berkeley, where I had some time to do some things. And well, maybe I go quickly through that. It's getting indeed a little bit nerdy, but on this time series analysis. But I just want to show you the principle quickly, if it hasn't become clear already. So suppose that we have three variables, and these variables create an external forcing just by a nonlinear, let's say, multiplication of these variables. And then this forcing basically causes another variable to be forced into a different state. This is here in this equation, so this y is basically quite persistent. It's like the old y, but then with some perturbation that is coming through this external forcing. And then we have an observable that is when the third variable comes on top. This is how this looks like. You have three different variables, x1, x2, x3. You see the x3 mimics a bit of a seasonal cycle. And then you see here, this is the forcing that comes through this multiplication of these three variables. And you see, for example, here, x1 is quite high and x2 as well. So here we have a strong peak of a positive forcing of the system, and that then leads to a pushing this observed variable, so the state variable up. But it stays up for a while because of this persistence here, and then it goes down after these variables are negative. Again, the forcing is negative again. So just actually a very simple dynamic system. And if you try to model that, or basically now the challenge is basically you just have variables x1, x2, x3, and you want to predict this one. This is kind of the challenge. And if you do that with a classical regression approach, trying just relate this to this, of course it doesn't work, and you can show that it doesn't work. And also classical feature generation methods like, oh, I take the lagged X to predict what's going on, or I take accumulated X, doesn't really work. If I would know what the forcing is and then I accumulate the forcing, then I can actually get a quite good prediction of the dynamics, but still deep learning method like a recurrent neural network is actually much better. And usually we don't know actually what is the latent forcing basically in the system is. And that actually is irrespective if you, for example, for the classical machine learning, if you use random forest or a neural network, it's always the problem that if you don't know the right features and they are not so easy to find, then we don't manage, while a recurrent neural network can just do it without generating any hand-designed features. So this is a relatively, even a very simple method, simple problem, and it's no surprise that such a method can actually do it. And I tried actually another example, and here are some ecologists in the room, I think, so that might be interesting. So there's this very simple other map, which is a nonlinear map, a logistic map for growth, that you can basically see here the equation, and depending on this parameter, on the growth parameter R, you get quite different dynamics from nothing to now so-called limit cycles with just going up and down, and then if these parameters going up further, you get limit cycles that are becoming more and more, let's say, complex and frequent, and at some point then the dynamics actually become totally chaotic. And what I did here, basically, I had this kind of random walk of this parameter before, the same equation before, so that varies a bit, and that is now the parameter of this growth parameter, which I put then into this equation. And what happens as a dynamics is that depending on this, on how this parameter is, so if it's relatively low, we don't get strong dynamics. If it's getting higher here, above 3, then we get here this limit cycle. So it's kind of dynamically adjusting the dynamics, and the question is basically if this relatively, well, it's still simple, but it's a complex model at the end, and the behavior can be mimicked by a recurrent neural network, and actually it was it worked out very well to predict the dynamics with such a network. So that was a bit nerdy, but it really convinced myself that there's a lot of potential in these methods to predict dynamics. Another very much nicer example from a PhD student in our group is now related to spatial context. And the question is basically here that we had if we can predict whole landscapes as seen from space. So we have, and predict means basically we have some information about the climate, mean temperature, precipitation, something on the geology, a little bit on land use and cloud cover. And can we basically predict the landscape from that? And indeed, we can. So this is basically reproducing a Sentinel-2 image just using this information that is usually at coarser scales. And the fine scale coherence in the picture, so the geostatistical properties can be actually extracted, or the mapping can be extracted with a so-called conditional generative adversarial network that basically maps all the variables here into a probable distribution, including the spatial dependencies of such a landscape. And here just some other examples. So these are actually now in the training data set, in the test data set. So these are real predictions, if you want. The observed Sentinel-2 images and the one that the system is predicting based on the information of climate and geology. These are, of course, good examples. There are also some bad examples, but overall one can clearly show that these kind of methods that use spatial context are very well suited to predict these spatial structures that are actually existent on Earth. But okay, one major limitation, and now I'm coming to the key points also of, if you want, of the talk, is that these are kind of black box methods, and the limitation is really that we don't understand actually how the system actually does predict that. It's a little bit opaque, and also physical consistency is not guaranteed at all. So the question is really that we as scientists will ask, if you're a physicist or biologist or chemist or geoscientist in general, should we really throw away all the knowledge and just let these machine learning methods do the job? And the answer is clearly no, because there are a lot of issues with extrapolation and a lot of possible failures of purely data-driven methods as well. And I give you just one or two examples how I think this can be actually linked together, or how we can actually gain understanding from applying these machine learning methods or deep learning methods. So one thing is trying to understand if ecosystems do actually respond dynamically to climate, for example, and at which time scales, and just maybe to clarify what we call here memory effect, which is maybe a little bit metaphoric. These are time-varying properties which depend on the past and possibly latent variables. And these are usually described in these Earth system models with differential equations or time-discrete analog equations. So an example would be that the vegetation development phenology depends on cumulative temperature over winter and spring. So we need to know what's going on in May. We need to know what has been happening in March and April, for example. Or if we talk about water balance, soil moisture is basically just coming from the balance of precipitation minus evaporation and drainage, and then of course integrated over time. So that also depends on the past. And I was mentioning already recurrent neural networks. This is exactly what recurrent neural networks are built for. They basically transform an input sequence here, these x values, into a hidden state. So that's a kind of internal state of the system. And then the output of the system, like the behavior of the system also, is then basically a function of the hidden state and the input variables itself. And this hidden state is something that is developing. So this state here depends also on the x variables before, because they basically go here through this sequence of those hidden states h. That's basically all. And you have a lot of parameters. I don't go into detail of neural networks, but you have parameters, the weights, that tell you basically now how the different neurons interact with each other. So one target variable that we were trying first is actually to try to predict the vegetation state itself, so as measured from remote sensing. So the target here was just the fraction of absorbed radiation, so kind of the greenness over Africa. And as a kind of test case, we tried to predict this greenness of the vegetation either with a random forest, so classical machine learning method where some lagged and cumulative water variables were included to have these hand-designed dynamical features. And second, with a recurrent neural network where only standard meteorological drivers and vegetation type, so no further kind of hand-designed features have been included. And what turns out with a almost blind approach of this recurrent neural network, one can actually predict the dynamics, the seasonal dynamics as well, and even slightly better than with a very, very hand-designed random forest approach with a quite high R square here if we aggregate that into ecoregions. But this is still just a black box approach. But again, we don't know what's going on. So to get insight, scientific insight, one idea could be to detect these memory effects with permutation experiments, and that's very simple. Also, we basically start with a time series that is in the right order, where the neural network can basically access the information from the past and compare that to the performance of the neural network when we shuffle the time series of predicted the time series of target variables and predictors. They are basically together, they are shuffled, and so the neural network cannot extract any information on the path because everything is mixed. And then the memory effect is kind of defined as the error with permutation minus the error, prediction error without permutation. And then one can also shuffle within blocks so that parts of the time information can be still accessed by the neural network by always keeping 2 or 3 or 4 or 5 consecutive time steps together. So, and so that way we can get insight on where memory effects play a role, and it's a very general method, so one can usually not blame the neural network because this neural network is very flexible. So if it has access to the information, then it should also extract the information almost perfectly. If it doesn't have the information, then it cannot extract it, and that's how we then come to this here, a map of the memory effect. So you see here many red areas, which are the areas where the prediction with including memory effects has been much better, and these are then areas, often semi-arid areas, where these effects play a very important role. Just one example of how to use those methods also to get insight into the systems and not just for black box prediction. But it still doesn't relate so much to the Earth system models directly. So I would like to come to this kind of concept that is also in the paper, where we really need to integrate model data, but also data and machine learning together with the modeling. And it basically starts with a view on the typical system model. So you have some input, you have submodel 1 that produces some output. This is input to another model, so that could be, for example, atmospheric model, precipitation, input to a land surface model, and the land surface model works with this input, has some parameters, and gives then as output, for example, photosynthesis or vegetation growth, and so on and so forth. So that is kind of a general scheme. And you see here that we have identified several instances where machine learning data-driven science can interact with a classical system modeling approach. One thing is actually to try to emulate the whole system that's being done. I won't talk too much about it, but trying just to emulate the whole model, which can be then very much faster executed and be used for uncertainty analysis and so on and so forth. One could also say, well, instead of taking this input that is coming from another model, which may be wrong, we just take output from a machine learning model where we have higher confidence that this is more realistic as input to the submodel, so that would be kind of uncoupled. Very classical, this is basically just model evaluation. Residual analysis can be also helped with machine learning at different levels, so that's what we call pattern-oriented model evaluation and calibration. So instead of just making a scatter plot looking at more higher order patterns that can be extracted with machine learning. And this is maybe the one that is most interesting and most challenging, where we argue one can try to replace completely one submodel with a machine learning model. For example, a submodel where we have actually very, very little theory and knowledge about. And it's kind of similar if you talk about parameterizations of models. We have basically a similar thing where often these parameterizations are done by semi-empirical meta models. They could be also this could be also done by machine learning. And one example, actually I'm not an expert in that, but it's very much done followed now in the atmospheric community, because we have these large grid boxes there of 100 times 100 kilometers. Where this heterogeneity, for example, of clouds is represented by a single value, if you will. So what is being done in the climate community, somehow that these kind of heterogeneity needs to be represented on a coarser grid. That's called coarse graining, because this is computationally prohibitive to run everything on a very high resolution grid. But this is based on rule of thumbs almost. And if now there are high resolution models becoming available, then one can, and you have a lot of data, then you can actually use machine learning methods to do, to learn the mapping basically from this part to this part, and learn the parameterization basically directly from the high and coarse resolution approach. And that seems to be working quite well, and there are a lot of promising results. If we talk about biological processes, it's more the idea that is now depicted in a more like, the previous figure was more like system oriented, this one is more deep learning oriented, where you have different layers of processing of data. Like you get simple features and you get more abstract features. This is a typical hierarchy of deep learning. But where we say, well, and then one can replace one of the deep learning layers, you can replace with a real physical model. Let me just go on the right-hand side, which is related to, for example, modeling evapotranspiration and stomatal conductance. So we have an input of climate forcing, and we know how water evaporates from the leaves to the air. That's typical. It's just a diffusion equation and depends on the energy balance. But what we don't really know so well, how the diffusive resistance that is coming from the stomata is actually responding to past climate, past weather, and the current weather. And there are, of course, a lot of empirical models. There's also theory about it, but it's not so clear what the plants really do. And so one could replace any same empirical model with a actually totally machine learning driven model that is here again a recurrent neural network to predict the sequence of stomatal aperture, and then apply again a physical model so that mass balances are okay and so on and so forth, to then predict, for example, transpiration and photosynthesis. Okay, I've been a bit slow, so I will skip that. It's basically just another explanation, a little bit more detailed. And I think I give you one last example. It is on respiration modeling. Where again this hybrid modeling may play an important role. We have some first examples here. So basically the respiration of an ecosystem is quite complicated, but it can be described as a simple multiplicative thing. So on the one hand there's a temperature dependence expressed as a Q10 function, and then biological base activity, this base respiration, that can be a function of all kind of potential factors like overall activity of the system, soil moisture, and so on and so forth. So that's kind of how one can look at that. And if we just relate the respiration to the air temperature, you can actually see different relations. And what has been done in the past is that, for example, the temperature sensitivity, this Q10, has been derived just from the data. So that's actually bad data science, if you want, and then you get a high Q10 for some systems and a low Q10 for other systems, but it's just caused by a confounding effect that at high temperatures you have, it's summer and the systems are anyway active, and that pushes these triangles up, while in the Mediterranean system it's the opposite, it's dry and it pushes them down, and the real response will be rather probably something in between. So one has to look at that. We have been looking at that by looking at different time scales of these responses. I will also skip through that. We've actually found that the Q10, or this temperature sensitivity, is quite stable, and now we wanted to look at what happens if we try to model that also with this kind of hybrid approach. On the one hand, we have this equation here, that we had before, and then we say, well, this temperature dependence we kind of know, but we only need to estimate the Q10 parameter. But we don't really know how the dynamics of RB, of the base respiration, the biological component, is generated. So we have some variables here, let them process through a neural network, another recurrent neural network variant. And then basically from these two models put together, the machine learning model, the, let's say, more physical model, the temperature dependence, we then get a prediction of the respiration. And what we actually do get, if we then estimate, we retrieve basically this RB parameter. This is our old results. Again, a kind of hand-designed analysis. And that's what we get from the machine learning approach, very similar dynamics. But on top you see actually here quite some variation. Here's a straight thin line, here it's going up and down, and this is actually the diurnal cycle. And this machine learning hybrid approach actually extracts even the diurnal cycle of the base respiration, something that we prohibited in the other approach because then there was not enough information. And the diurnal variation even it even makes sense. For example, in summer we have a stronger diurnal variation of RB than in the winter time. It's speculative, but for sure what we can also say that the predictive ability of this new hybrid modeling system is much better. So we have unbiased diurnal residuals, while the old approach that just ignored potential diurnal dynamics actually does have this kind of biased diurnal cycle. So again, one can improve models, one can learn about the system. In this case, we can speculate that there is another diurnal cycle of the biological activity. So last slide is really more like a general wrap-up. I'm not going to say, I'm not saying, and that data-driven science solves everything, but I think we should have a more general and open view how we do science and integrate basically on the one hand the classical hypothesis-driven science where we have existing knowledge, some hypotheses that we put together into principles, process knowledge or theory, and then implement in some model, like a climate model or so. Then we have predicted patterns that we derive, so that's kind of deductive. And then we see if we can find observations to confront the model with these observations. And this is a classical way. The other way is actually to start from the observations and say, well, let's see what kind of products we can actually derive from integration of different observations, extract and recognize observed patterns, and then from that try to see if these patterns make sense, if they are trivial or not. And if they are not, we can generate hypotheses that may explain these observed patterns. And at the end, actually, we have a full cycle that actually makes up science. And the interesting part is really then coming here in this triangle between the model predictive patterns and the observed patterns. And what I say is, if we find certain observed patterns, we can only say, oh, this is surprising, if we compare that to a state-of-the-art model. If the state-of-the-art model shows the same patterns that are emerging from the modeled interactions of the systems, then it's actually not a surprise. But if we have really substantially different patterns, then we have learned actually something, and we have to work on hypotheses how that will then lead to improved models. That's a bit the general view. I would like to make one advertisement. If you're interested more into this, actually we have been able to attract the machine learning community, which is vast. Okay, sorry for this. And who have basically established a European lab for learning and intelligent systems, all kind of different aspects, robotics, of course, autonomous driving, all these things that one is hearing about. But we have been convincing them to have as one key topic also machine learning for Earth and climate science. Gustavo Camsovals and I am leading this. You see here some of the goals that are reflected also in the talk. So contact me or Gustavo if you want to know more about that. There's some list of initial fellows, but it's an open program and you're invited to come to workshops and so on and so forth. And if you're interested in more work related to the climate science and what's going on in the Max-Planck Society, I also... Okay, that's in German, but you can look into these actually quite well done booklets of the Max-Planck Society on this context. Thanks a lot.